Hello everyone, and welcome to Lab Manager's Product Spotlight webinar series. These webinars are designed to help attendees understand a specific proprietary service or technology and where and how it can be applied in an effort to help labs operate more efficiently. My name is Trevor Henderson, and today I'll be moderating our webinar titled Better Rheological Results, What to Do Before Pressing the Start Button. We like our webinars to be very interactive, so we encourage you to send us your questions at any point during the presentation. Many of you know the drill, but for those of you just joining us, you can ask questions simply by typing your query into the question box, which is located on the bottom left-hand side of your screen. We'll try to address as many questions as possible during the question and answer session, and if we happen to run out of time, I will forward any unanswered questions to our presenter, and he can respond to you via email. Additional resources can be accessed via the resource window or via the resource icon located at the bottom of your screen. And you may also move or resize any of the open windows simply by grabbing them at the top or stretching them at the bottom right corner. At this time, you may need to move or minimize some of the open windows to see the live view. This webinar recording will be available early next week on Lab Manager's website. At the end of this webinar, we'll share that link with you as well as the contact information for our speaker. With that, at this time, it's my pleasure to introduce today's speaker, Nathan Crawford, who joins us today from Thermo Fisher Scientific. Nate is the Rheology Application Specialist for Thermo Fisher Scientific in the U.S. and Canada. He has a PhD in chemical engineering and over 7 years of experience conducting rheological measurements. Nate has worked with a wide range of materials from colloidal suspensions, biomass polymers, food, and beyond. Nate, thanks for joining us today.
Perfect. Thank you, Trevor. And thank all of you for attending today's webinar series. And as the title suggests, today's webinar will be essentially a guide to better rheological results. Today, we hopefully, moving forward, we will help guide you to avoid the common pitfalls that come along with taking rheological measurements. And then hopefully moving forward, you'll feel more confident with the data you gather using rheology. So a brief overview of what we'll cover today. First, we'll go over why in the world would you want to actually use rheology in the first place. Hopefully many of you are either currently using rheology or thinking about adding rheology as part of your analytical suite in your labs. So you probably have a good idea of why, but possibly today we'll give you some added information to help kind of fortify your interest in rheology. And before you do a rheological measurement, it's crucial that you select the right measuring geometry or tool, rotor, spindle, for actual material for the job you want to perform. Then we'll move from the selection of the geometry to actual handling the sample properly and loading it into the rheometer. And then from there, we'll discuss how you can actually improve the measuring procedure itself. So the first question is, why do you want to use rheology? And as a self-proclaimed rheologist, I'm a bit biased, but rheology is everywhere, okay? It's in all the materials we use from every aspect of our lives, from all the cosmetics and toiletries we use this morning as we're getting ready for work, from our toothpaste to our shampoos, our liquid soaps. It's in the food we consumed day in and day out. It's in the clothes we wear. It's in the vehicles that we take to and from work. It's in all the products we even use at work. Potentially some of you could be taking notes today. It's in the inks that you use in that pen, or perhaps the adhesive in the back of a sticky note you could be writing notes on. It's also in the inks of inkjet displays or inkjet printers. But all of these materials have unique rheological profiles. And they're intelligently designed and engineered to display these rheological behaviors under certain conditions, applied stresses, strains, under different temperature conditions. So essentially, they exhibit the designed rheological behaviors and have the proper profile for that material's intended end use, so that us as the consumers that we're using that product behaves as we expect for optimal performance. So rheology is not just important at our end product, okay? Rheology is always important throughout the lifetime of that material. So it's crucial before, during, and after the production of that end product. So before, so all the raw feedstock materials you get at the lab or at the production facility, let's say you get those materials from 2 different suppliers. We want to make sure that even though you're using two different suppliers, that same material that they're delivering is equivalent rheologically. Let's say you're getting one supplier of material, but you want to make sure that lot A is equivalent to lot B. Well, you can use rheology to make sure that material is consistent from supplier and from different batches of different lots. And then as you begin to produce this end material that you're going to use, during operation, you want to make sure that the different process blocks are behaving properly. They help you set up operation as well as design that individual process. So from pumping, mixing, stirring, reacting, extruding materials, you need to know the individual rheological profile. So as you add a material, let's say to a reactor, it may enter that reactor as a liquid and come out at the other end as some sort of solid. We need to understand how that material is actually going to flow from the start of that reactor to the end. Then when it comes out of that process unit, how do you transport it from the first process unit to the next? So how do you actually pump and move and transport materials? So the rheology profile is very, very important when you actually set up these process blocks. And then once you have your final material, you need to make sure that the material is exhibiting the physical and mechanical properties of its intended end use. And those intended end use, those mechanical properties are suitable for the end user and the desired application. So rheology is everywhere. It's in all the materials you use. And it's always important regardless of the stage of life of that material, from the beginning to the end and throughout its intended end use. So before you actually set up a rheological measurement and start to probe some of these material properties, the first step in a rheological measurement is making sure you select the right measuring geometry or rotor or tool to actually interrogate a material. So with rheometers come with a wide range of possible measuring geometries. Some of these are quite standard, you've probably seen before: concentric or coaxial cylinders in the top left, or Conan plates, or parallel plates, the most common. Sometimes you have more exotic attachments, like vane rotors or pin rotors, or even these textured or profiled surface we can grab onto more robust or higher, larger particle samples, or even setups that actually deal with solid films. You have bending and breaking type tools, or extensional type tools, or torsional tools that actually test solid films. So typically the new user to rheology gets overwhelmed and asks the question of which one should I use and which one is suitable for my material. Well, it really depends. It depends on the type of material you're working with and the actual material properties that you're trying to characterize or interrogate. So most people just get overwhelmed. And so then they go down the path of, can I just use a single measuring geometry for all of my applications? The simple answer is no, okay? Unfortunately, there is no such thing as a universal measuring geometry. You can't just load a single setup and that'll work for all materials, from your flowable, easily cleanable, pourable, low viscosity liquids, all the way up to your solid thin films, okay? Each geometry, each test method needs to be designed for that material itself. So the first step in picking the actual geometry that you should use for your material is quite subjective, but you need to start by first visually inspecting your sample, okay? If you have it in a storage vessel, and hopefully you can see through that storage vessel, you start to, tip it, swirl it. Is that material flowable? Is it pourable from that vessel? Or is it more of a paste or gel-like that just sits as a solid sludge at the bottom of that container? Is the material sticky? Does it appear easy to clean? You can even poke it with the end of a pipette. How does that material respond to that poking? Is the material stays separating in that storage container? Do you have a solid particle bed at the bottom, which is just a solid mass, and some liquid that sits on top? How does this material behave? Well, after giving this general visual inspection, you need to consider the viscosity, the general viscosity of that material, and the sample volume that's available. If it's a rather low viscosity and you have somewhat large sample quantities, you typically want to start with coaxial cylinders. So those are typically work with low viscosity, meaning close to water, slightly above, to the medium range, let's say around olive oil, and even a little bit higher. Those materials are quite simple, easy to flow liquids, or easy to clean, like a water substrate would be, or even some oils. The coaxial cylinders are the best option. However, even if you have a low viscosity material, but it is sticky, let's say some sort of sugar solution, it's difficult to get out of that coaxial cylinder. The cone and plate or plate and plate type setup is probably a little bit better. If it's going to be probably medium to high viscosity, that's ideal for the cone and plate or plate and plate. And if you have a limited quantity sample, let's say a 1 mil or less, that's not going to be suitable for the coaxial cylinder, so a cone and plate or a parallel plate type setup. If it's a homogeneous sample, relatively simple, a solvent, an oil, or even a simple emulsion, the cone and plate is acceptable. If you start adding particles to your material and it's more of a suspension or even a thick paste or gel-like material, then you're probably going to have to use the parallel plate setup. If those particles are even larger, let's say a 0.5 millimeter, possibly larger, maybe multiple millimeters, if those particles are heavy and dense and they begin to settle out, you have to use some specialized geometries like a vane rotor. Vane rotor to me looks more like a boat impeller. Okay, it has blades on it. Those blades actually grab onto these larger particles or these thick samples, be able to grab onto them and be able to shear them. Okay? Now, a general rule of thumb is for lower viscosity materials, as you approach materials like water, even like gasoline, at very low viscosities, you're going to have to use larger surface area rotors. Okay, so concentric cylinders or coaxial cylinders have the highest surface area, so those are going to be most ideal and most suitable for low viscosity materials. If coaxial cylinders aren't appropriate for your material, then you can use a cone and plate or a parallel plate setup with the largest diameter you can find, again increasing that contact surface area for your low viscosity materials. But as you go up in viscosity, you can transition to cone and plate or parallel plate, and at the higher viscosities, it's going to be most likely a parallel plate setup. So rule of thumb, low viscosities, concentric cylinders, medium to low, medium to high, cone and plate or parallel plate. Okay. So first, looking at coaxial cylinders, and this is the most commonly used geometry to do a rheological measurement. They're quite simple. As you can see here, this is essentially an outer cup. It's a vessel. Essentially, you load your sample in there. The sample is depicted in red in these images. And then you just submerge an inner cylinder or a bob rotor inside there, and that rotor spins, and you measure viscosity. Okay? Because of its large surface area, it's very sensitive, so like we said, it can work with low viscosity materials. And it's very simple, so it's commonly used. There's lots of historical data. You can use very simple instruments with this type of setup. You use a simple viscometer that you attach a bob and it rotates at a single speed. You can measure viscosity relatively easily. Not very sensitive to sample volume, so if it requires, let's say, 10 to 20 mils, and you add a half mil or a milliliter too much, it's not going to greatly affect your viscosity measurement. So they're good for a quality control measurement when you can't add precise amounts of sample. And they're commonly used in several standards to measure viscosity of certain materials, ISO or ASTM type standards. So these the concentric cylinders are the closest thing you get to a universal measuring geometry that is so widely used. However, some of the disadvantages to this type of setup is they're very difficult to use with higher viscosity samples or samples that have yield stress. So it's just hard to actually get this bob down and through the sample that's very, very thick. A lot of times you'll actually begin to pre-shear your sample as you insert that bob. And a lot of times you'll disrupt your sample and it won't actually relax and reform. So you get this discontinuous contact between the bob rotor and the interface of the sample. The geometries of this type of setup, say the diameter and height of your inner and outer cylinders, are predefined, so you can't change the gap spacing or the dimensions between your inner and outer bob. They can be very challenging to clean, so if you have a very sticky, thick sample, it's hard to actually get into this cup sometimes and clean it fully. And because you're using higher sample volumes, it takes a long time for the sample to reach thermal equilibrium, sometimes 15, 20, even 30 minutes to get up to the test temperature. And because of that, as you can imagine, if you're doing some sort of heating or cooling ramps, changing temperature during your measurement, it can take a very long time to change the actual test temperature. So that can be limiting with using the concentric cylinder type geometries. So the other options here are to use either a parallel plate type setup or a cone and plate. Okay? The cone and plate or parallel plate setups, they use much smaller volumes, somewhere between 1 to 2 milliliters, a lot of times less. So if you have a very limited sample supply, most likely you're going to have to use parallel plate or cone and plate. Because you're using less volume, you can reach equilibrium within your sample thermally much quicker. We're talking about 1 to 5 minute type time ranges to actually get your entire sample up to that test temperature. Because this top plate or cone basically separates entirely from the bottom plate, and just cleaning those two surfaces, it's much easier to clean. You're just cleaning the bottom surface of that cone or top plate and then the top surface of the bottom plate. And if you're using the parallel plate setup, that gap height can be adjusted. So you can actually decrease the gap spacing to accommodate even lower volumes of your sample, or interrogate your sample at actually higher shear rates because you're changing the gap height. Or you actually increase the gap height as well within your parallel plates to accommodate for larger particles or larger sample volumes as well. So some of the disadvantages with the cone plates or parallel plates is that they're a lot more sensitive to sample volume. So if you slightly underfill this by a tenth or even 2/10 of a milliliter, underfill or overfill, that's going to really impact your viscosity measurement. And this outer edge on both the cone plate and parallel plate setups here, they're very susceptible to evaporation or drying out, which will again impact the measurement. And when you're operating at high shear rates or shear speeds, or you have samples that are kind of highly elastic, like a polymer melt, they tend to actually leave the gap. You can actually fling sample out of the gap between your parallel plate to your cone plate during the measurement. And then working with the cone plate, that gap is fixed based on how that cone is machined and engineered, has defined set gaps. So you can adjust that gap height to accommodate different sample volumes or particle sizes. So the cone plate is slightly more limited than the parallel plate setup. So here's actually an example, some example data using a sample that contains particles. It happens to be actually a smoothie with some seeds or some actually fruit particles that were left over after the blending. We measured its viscosity both with the 35 millimeter cone with 1 degree as well as the 35 millimeter plate. So first looking at the cone data, which is the triangular data towards the top, you can see here the stress response is in blue. You can see the stress jumps around quite a bit. What's happening here is that cone actually has a fixed gap of 52 microns. And so these seeds within the smoothie are actually getting stuck in the center of that cone and getting jammed, and they begin to just grind. And so as the cone begins to rotate, it's basically getting stuck and then accelerates, decelerates, accelerates, so you get a lot of noise in the data. And so what's going on here is essentially the particles at the tip of the cone are just grinding, okay, and it's really affecting the quality of this measured data. However, if we move over to 35 millimeter plate, which now has a gap height of 1 millimeter, much larger, it can actually accommodate these larger seed particles. As you can see the filled red circles, you get a much smoother viscosity response. And again, looking at the stress response here in the blue circles, this data is much higher quality. You don't have the same noise because those particles aren't getting jammed. Okay? So the larger gap allows you to just obtain higher quality data. So always remember, if you have particles with size, if you have a sample with particles, always consider the maximum and the average particle size, and making sure that you select an appropriate geometry to measure that viscosity. So a good rule of thumb, if you know the maximum particle diameter, you want to work with a gap height of about 5 times that maximum particle. If you know the average particle diameter, then you want to work with 10 times the gap of the average particle diameter. So let's say you have a maximum particle diameter of, let's say, 10 microns. Well, 5 times that would be 50 microns. So the example on the last page with the 52 micron gap for that cone would probably be acceptable. However, let's say you have an average particle diameter of 20 microns, well, 10 times the 20 micron particle diameter is now 200 microns. So that cone at 50 micron truncation gap is no longer acceptable. So you'd have to use that parallel plate to set up at the 200 micron gap or larger. Okay? So always remember that the cone and plate geometries or the concentric cylinders, those gaps of that geometry, the dimensions are fixed. You can't adjust those. But for a parallel plate setup, you can actually adjust the height, adjust the gap to accommodate different sample volumes or particle sizes. If you are using sample with large particles, Again, you can adjust that parallel plate gap height, or even potentially the cone angle. If you use a larger cone angle that comes with a larger gap, that might be suitable for your sample. If the particles are really large, you may need to go up to a textured or shear-rated plate where actually you can grab onto those larger particles and be able to shear them, or sometimes even larger particles up to, let's say, half a millimeter, even multiple millimeters. You may need to use a vane-type rotor. So another option, if you've physically inspected your sample, you know the approximate viscosity of the sample, and you know that you want to use a parallel plate versus concentric cylinders. However, you want to know exactly what is the ideal or proper plate or cone with the proper angle for your material or for the shear rate range you want to investigate. Well, with our thermoscientific rheometers and viscometer products, it comes with our Reoloji software. In the Reoloji software, we have a range calculator that actually calculates the range at which a given rheometer can actually measure viscosity. So you start by selecting in this drop-down window the instrument that you're using. Here's the VTIQ, and the measurement geometry you want to use or you're currently using. Here it's the concentric cylinder, 25 millimeter diameter setup. And then you want to input the actual sample viscosity. Let's say you have an idea. Let's say you know it's close to water or 10 times water, or maybe you have a range of viscosities you want to look at and you want to have one geometry that can cover that whole range. We can enter multiple viscosities in here. And then the software automatically calculates the actual measuring range of that rheometer with a given geometry. So, and it gives that, reports that range in two ways. First, numerically. So it actually gives you a shear rate range. So with the VTIQ, the 25 millimeter concentric cylinders, you can operate at a shear rate range about 0.45 up to 226 reciprocal seconds. Also reports the shear stress range. The software also shows it graphically. So over here down towards the bottom, a plot of viscosity versus shear rate. The actual measuring range is outlined here in blue. Now you input a viscosity of 10 Pascal seconds. It's actually represented in this green line here. So you're measuring the material with a viscosity of 10 Pascal seconds. This is the operating space for that viscosity. Software even takes it a step farther, is you can actually input an exact shear rate which you want to interrogate this material at. Let's say 10 reciprocal seconds at 10 Pascal seconds. It actually shows that measuring point on the graph here. So you're measuring a 10 Pascal second viscosity at 10 reciprocal seconds. This is where that measuring point would fall in the overall range of that material, or that rheometer. If this X or asterisk falls outside of this blue measuring range, you know that you're going to have to adjust and use a different measuring geometry for that material and at that shear rate, or possibly even a different instrument. So this range calculator really eliminates the guessing factor. Okay, so you don't have to actually load a sample, test to see, okay, is this geometry appropriate for my material and the shear rate range that I want to interrogate. And so by doing so, you save time, material, you're not loading, wasting time, cleaning up, loading a different sample, changing the geometry. And then it helps you really ensure that you're using the optimum geometry for that job. Doing this kind of visual inspection like we talked about before can get you good or give you a good idea of what geometry, but it won't actually pick what's best. So, is this the ideal plate radius or diameter for my material? Is this the right cone angle? Okay. So this range calculator really helps you hone in on what's the ideal geometry for this setup. So now that we've learned how to properly select the ideal or appropriate geometry for a wide range of materials, now we need to go into how to actually handle our sample and get it from the storage vessel into the rheometer. So if we're dealing with simple liquids, oils, solvents, water, there's no special tricks for those. Those are easy. You're going to use a pipette like you've all done multiple times with different instruments throughout the lab. However, it gets much more tricky when your sample is more complex. Most of the time in the lab when we're doing rheological measurements, we don't have simple liquid samples. We're more going to be more robust, complex structures. And when we have these structured samples, we need to make sure we handle them with care. Okay? So when we're transferring them from the storage container into the rheometer, we make sure we do that very carefully. Right? These samples that have structure, don't shake them, stir them. Okay, that will break up their structure, potentially introducing air into them. So don't squeeze them through nozzles. Don't use pipettes. Don't use syringes. Those syringes, squeezing them through a nozzle, actually pre-shears them. Okay, so that shearing could disrupt the structure, and depending on the material, if it breaks down irreversibly, you can't regain that structure. It's best to really use some sort of spoon or spatula, scoop out that material, gently place it on the bottom plate, that's depicted in the picture on the top right, and then carefully place it kind of in a circular pattern along that bottom plate. Don't squeeze it, don't smear it, don't use the back of the spoon to spread it out. Just let it kind of gradually, carefully flow onto that bottom plate. And then when you want to actually lower the top plate or cone onto that sample, make sure you're doing it very, very slowly and carefully. Okay, so within ReoWin, the rheometer software control, we actually have a lift element that you can put into your measuring procedure, and you can control the speed at which you lower that gap. Okay. And then if you lower that gap slowly, have your sample well dispersed, make sure that you allow suitable recovery time so that if you apply any mechanical force as you squeeze that sample between the two plates or the cone and plate, that you allow enough time for that applied force to kind of sample relax after shearing or squeezing it. And then you make sure you allow enough thermal equilibrium time so that your sample reaches test temperature, not just part of the sample, but the entire temperature. The entire sample is at the test temperature. Okay. And so when closing the gap with reduced speed, we understand it takes more time, and sometimes, a lot of times in the lab, time is of the essence. Depicted on the right is a graph showing the gap height and the actual time it takes to close the gap height. So in blue, you can close the gap fast, so you're going from, you're going to load your sample at 10 millimeters, close the gap rapidly, going from 10 millimeters down to 1 in about 10 seconds. Okay, that's pretty standard. However, we recommend going much slower. So going from, let's say, 10 millimeters of your loading gap down to 3, you can do that relatively rapidly, but then slowly decreasing from 3 millimeters down to 1 millimeter to your test gap height to make sure that you're not disturbing the sample. This takes about, let's say, 4 times longer, but still, in the grand scheme of things, this is still, you're lowering the gap, you're lowering that measuring head in less than 60 seconds. So that overall, that 1 minute is well worth it. Okay, you're going to be confident that you cause less damage to the structure of that material. You don't have to have as much recovery time afterwards. So other than thermal equilibrium time, you don't have to wait to press go on your sample as long as you're confident you haven't destroyed its structure by squeezing it. You're reducing the risk of actually including air bubbles in your samples. So when you lower that head quickly, there's a good chance you could entrap some air, which will then affect your measurements. And then your actual measuring results could be affected by how quickly you lower that head. So on the next slide, we actually have some example data. This is measuring the yield stress of a lotion sample here. We're measuring the deformation on the y-axis as a function of input stress. So applying stress, initially the material is just deforming linearly as we're just stretching that material. And eventually we get to a critical point where we're stretching the material so much that essentially its structure breaks down, and it goes from deforming linearly to that structure being broken down, and it basically deforms exponentially. So we go from a static point where we're just stretching that material, then we break its structure and it begins to flow. And you can see that elbow in the curve, and that's essentially that elbow point is when it transitions from a static point to a flowing point, and that is its yield stress. This material, when we close the gap quickly, we measure yield stress at 8 pascals. However, if we do a reduced, much slower gap closure, pulling that gap slowly, as we talked about in the last slide, we now measure a yield stress that's close to 12 pascals. We see about a 50% increase in measured yield stress of this material by just changing how quickly we lower that measuring head. So by doing so, lowering that head quickly, we're actually disturbing its structure, and by already pre-disturbing its structure, we're reducing the measured yield stress. So by lowering that head quickly, we're actually already beginning to break down its structure internally. So if you are handling fragile samples in the lab, make sure you do that with care. And if possible, make sample preparation part of the measurement job. So as we saw before, proper loading the sample, you can actually have images or videos built into your procedure. And you can actually use the software to actually slow down the lowering of the head to make sure you're not pre-disturbing that sample structure. And so now you know how to properly transport the sample from this container onto the rheolometer and lower the head properly. We need to make sure you're actually loading in the right amount of sample. So luckily within the Reolin software, again, based on the geometry that you're using, and it'll actually calculate what volume of sample is required. So here this has the parallel plate, 35 millimeter diameter, and a gap height of 1 millimeter, requires a volume of just under 1 milliliter. Okay? So if we load a sample into our 35 millimeter plate, exactly right around 1 mil, this is what the sample should look like. It's up in the right-hand corner, depicted in red. And if we measure this viscosity of the standard oil with correct amount of sample volume, we should measure viscosity around 14,000 millipascal seconds. However, if we underfill the sample, overfill the sample by about 20%, depicted again by this green, you can see the sample has kind of spilled over the edge of the bottom plate. We now measure a viscosity that's slightly high, about 10% higher than its nominal viscosity. However, if we then underfill the sample by about 20% here in blue, so we have less sample than is required, so 20% underfilled. However, we measure viscosity that's more than 30% below its nominal viscosity. So by underfilling, you're actually leading to larger measurement errors. So when possible, it's always better to overfill than underfill. It's much more difficult to add sample than remove sample. Okay? So general rule of thumb, always overfill, never underfill. When you're working with parallel plate and cone type geometries, the key is to overfill and then trim off and remove excess sample. And within the Reolin software, you can actually use a trimming position. Okay? So you lower the measuring head, the top plate, the cone, to its trimming position, so slightly above the measuring position. You remove the excess sample with some sort of straight edge here along the outer edge right here. Be careful to make sure if there is sample that spills over onto that top plate that you also remove that from the upper measuring tool. And then once you're done trimming the sample, then you lower the head from the trim position, which is a height just above the measuring position. So move it down to the measuring position. And a properly loaded sample should have the slight convex or this bulge at the outer rim. Okay? So if the sample is properly loaded, trimmed, and at the proper measurement height, you should see this bulge. Okay? And that's ideal. So it's always crucial to make sure you check that you have proper sample loading before running the measurement. So even after you've loaded the proper amount of sample into the rheolometer, there's no guarantee that the proper amount of sample will remain loaded within your geometry throughout your measurement. Okay? So here's showing measurement of material. If you look at viscosity as a function of shear rate, here in the red data point, you can see that the viscosity is showing this nice shear thinning profile as we're increasing shear rate. However, you get to this critical point that shear rate's above 1,000 reciprocal seconds, and all of a sudden you see this drastic drop-off and reduction in viscosity. And it's mirrored by this just another drastic drop-off in the measured shear stress. Okay? So this is not a material behavior. Okay? This is a measurement artifact. And what happens when you get up to high shear rates is at times you'll actually eject sample from the actual measuring geometry. So here's a picture. You can say, if you look dead on here, you can actually see this void space in your sample. And the sample is actually this white material here. And out towards the outer edge of the plate here, you can actually see the sample's lost contact. You've lost material out here. And so when you see this drastic drop-off in your measured response, it's usually an indication that you've lost your sample. Okay? And that commonly happens when you're using cone and plate or parallel plate type geometries, especially when you get up to high shear rates or high stresses. And it commonly happens with plates when you're using a large gap. With cones, you have a large cone angle. With a larger cone angle, you have a much higher gap towards at the outer edge. Or sometimes when you have highly elastic samples, you actually lose contact, or you get what's called edge fracture at the very edge of your sample. And it commonly happens with polymeric melts. Okay? So to kind of combat this effect, if you're using parallel plates, you can use a smaller gap, okay, you can shrink down that gap, or potentially work with a smaller cone angle. If you have highly elastic samples, sometimes no matter what you do, rotation is going to be a challenge, so you can switch over and do an oscillatory measurement, or if applicable, you can also try using a cylinder geometry. So another way that sample can be depleted during during measurement is during drying out or evaporation type effects during the test. This happens a lot when you're doing long time measurements, say over 30 minutes to possibly multiple hours, or you're working at elevated test temperatures. All right, they tend to dry out the sample. As you can imagine, you're drying out, you're losing liquid. You can either dry out and harden your sample, or you're just losing liquid, and so you're losing sample volume. So it can either be an increase in viscosity or decrease in viscosity, depending on the material and its effect. So how do we kind of counterbalance some of these drying out or edge effects? We use what's called a solvent trap. This is depicted in the bottom right corner picture. You can see the payload plate setup has a little inner cylinder solvent trap. You load sample on that inner cylinder, and then that black half hood there is a half piece of a two-piece what we call our sample hoods. It basically enclose the entire sample environment. So you can load solvent on the inside. This hood actually dips down into that solvent. You're going to add solvent out towards this outer edge beyond the blue paper that you can see by the sample. And by doing so, you add that hood, which encloses the environment, and then the solvent that you add will actually saturate the local environment around your sample, so to actually limit any evaporation effects. Okay. And another common way to combat drying out on the edge is to add low viscosity oil around the rim of your sample. Okay, so again, that'll enclose the outer surface of your sample and keep it from drying out over time. Again, if neither one of those are an option, you can move over to a concentric cylinder type geometry if possible. Again, concentric cylinder geometries are less affected by losses in sample volume. Also, you can cover that sample with a little bit of oil again to conceal the sample and keep it from drying out and losing any volume due to evaporation. So now, throughout our rheological measurement, we've figured out how to select and ways to pick the proper measuring geometry for our material or for the method we want to use. We've learned how to properly handle samples, load them into the rheometer, trim them, and use the proper amount of sample, and then how to combat any external effects like ejecting sample or samples drying out. Now we're going to actually talk about how to improve your actual measuring method itself. So the most common rheological parameter that's tested is viscosity. That's the most common kind of metric that's used. And the most common test that's used, it's simple. It's just what's called a single point measurement. So you load your sample and you measure its viscosity using a single constant shear rate. Okay? Now this is acceptable only when you're dealing with very simplistic Newtonian type materials. Let's say pure solvents, oils, even water. Okay, they have a single viscosity regardless of the shear rate that you expose them to. And this is a very easy, quick test, and you obtain a number for the viscosity. And that's all people want is what's the viscosity. They want a single number and they move on. And if this test is done well, all the testing parameters are well defined or controlled, this type of measurement actually can measure an absolute viscosity for that material. Okay? So it can be an absolute measurement. It doesn't have to be necessarily relative. However, you don't get the shear rate dependence of the material. So most materials that we deal with in the lab are more complex than a single-phase solvent or some sort of oil. Okay, they're more complex. Their viscosity actually depends on the shear rate at which you expose them to. So they're called non-Newtonian material. The viscosity will change depending on exposed shear rate. So here's an example on this plot. And it's a plot of viscosity now as a function of shear rate. We have three different materials. We have red and blue materials that show pretty significant shear thinning behavior, so the viscosity is decreasing quite drastically as a function of shear rate. Then we have this green material, which has pretty long Newtonian plateau, so its viscosity is pretty constant until you get up to high shear rates, because you eventually see some shear thinning behavior as well. So if we use viscosity as our metric, and we want to know, okay, which one of these materials has the highest viscosity? Okay, well, it depends on that single point measurement. What is that single shear rate we're exposing materials to? If it's a very low shear rate, well, in this case, the red material has the highest viscosity, and then the green material has the lowest viscosity. But what if that single point measurement is done at the high end, so let's say your shear rate above 100? Well, at this point now it's opposite. The green material has the highest viscosity, while red is the lowest viscosity. So by doing a single point measurement, you're not capturing the shear dependence of these materials, and if viscosity, either high or low as your metric for quality control, are you testing that material using a suitable shear rate? So it's always important to measure viscosity over a suitable shear rate range. And that shear rate range should be applicable to either how that material is being processed or how it's going to be used as an end-use application. Okay? And always remember, when we're dealing with complex materials, viscosity is a full plot, not a dot. So you can't represent a complex material by a single point. Okay? So once people have evolved and they understand that we need to test the material over a range of shear rates, you usually go from a single point measurement into what's called a rotational ramp. You're just ramping the shear rate from the low end. Here it's from 0 all the way up to a high end, which is 200 picoseconds. So it's a predetermined window of shear rate. And you're ramping it over a fixed amount of time, typically 1 to 2 minutes. For this data set here, it's over a minute. And you're just measuring the viscosity response, okay? Highly reproducible, it's easy, it's quick, and you get what's called a fingerprint of your material. And the challenge with this is it's a transient measurement. So this is time dependent. And because it's time dependent, it doesn't give you an absolute measure of viscosity. It's a relative test. And it's a relative test only if you take two materials, let's say material A and B, and you measure them under identical conditions. So under the same time, using the same geometry, over the identical shear rate range, and you're ramping the shear rate in the same fashion. Okay, so the viscosity that you measure using this rotational ramp is dependent on your method. Okay, it's not an inherent material property, so it's a very limited measurement. Okay? So the next slide, we show what we call a real viscosity curve. So here is the shear thinning curve we've seen before. Viscosity is a function of shear rate. This is what we would say this is a good quality measurement of the shear profile. But if we show this next data set and we look at this same material, it's now the exact same material, now plotted here in blue and do two separate runs. Identical material, but you can see its viscosity response is entirely different. First we see a slight decrease in viscosity, then an uptick, and then eventually it follows the same viscosity as the red viscosity curve with the red data. And the same material again is interrogated here, now shown in green, and we see a third response where we actually see an increase in viscosity, then a decrease, and eventually see an overlap with the red data. So really the difference, we're seeing identical material, but the difference is actually how the method was defined and how it was used for these materials. So the red data, which we call our good or high quality data, is using what we call a stepped profile. So we're stepping the shear rate from the low end to the high end, and it's holding the shear rate constant at each interval, and it's letting the sample determine when it's reached equilibrium. So it doesn't move on to the next point until that sample has reached equilibrium, moves to the next. These other two measurements are just doing the ramp. So over a predetermined time, they're just getting from the low end to the high end over the set amount of time, and it's just distributing the data differently, either log fashion or linear fashion. It really doesn't capture the true behavior of this material because it doesn't spend enough time. Especially at the low end, you see a big difference in viscosity measurement with the low shear rate range. However, at the high end, we do see some overlap. So it's more suitable if you are measuring the higher shear rate range. So why is this? So really, it depends on how quickly the material reaches an established flow profile. So as we set a rotational shear rate or speed, the instrument reaches that speed almost instantaneously. Okay? But how quickly the material itself reaches a well-defined equilibrium flow profile depends on the sample itself, so how viscous it is, or if it has some elastic components, and then the shear rate we apply. So if we look at this plot, it's viscosity as a function of time, and the data in blue, if we apply a 50 reciprocal second shear rate, a rather high shear rate, this sample reaches kind of a constant viscosity almost instantaneously. So it's immediately at constant viscosity. So if we collect that data quickly or long, we're going to get the same viscosity measurement. However, if we reduce the shear rate to 0.005 reciprocal seconds, the same material takes much, much longer for that flow profile to develop, much longer response time. So even after this 3 minutes of interrogation, really that viscosity is still slightly increasing. It hasn't really reached an equilibrium state. Okay? So really we have to match how we're collecting data to the time response of our material. If you're working with low shear rates, relatively higher viscosity, you need to give enough time for that that flow profile to develop and collect high-quality data. So within the Reolin software, you can actually set up so that the instrument itself determines equilibrium automatically, okay? You do this in the acquisition tab. You can select the gradient. So this is really just selecting how much the material can change, which we consider this equilibrium, okay? So we set the gradient value at about 5% here, okay? So it's saying that if our material response here being stress or torque changes by less than 10 or less than 5%, then it's reached equilibrium. Also in the software, we can set a delay. So we know that the initial data points, we know that the material is going to take a little bit while to reach this equilibrium point. So we're not going to even bother with the first 3 seconds of data. For this material, because it develops much, much longer, we can even set this delay to 10, 20, even 30 seconds perhaps. You can adjust that. Then you can set the max waiting time. So you can wait to see how long at each point. If it doesn't reach equilibrium within 120 seconds here, which is 2 minutes, you can even set it up to 10 hours if you want. And if it doesn't reach equilibrium within that, it's just going to move that time to being named. It's going to move to the next shear rate predetermined window. And then you can determine how you're going to acquire data. So the material response, it's changing by less than 5%. Okay, it's happening for 3 seconds. I'm going to integrate over that 3 seconds. It hasn't changed by more than 5%. You're going to integrate that data and move to the next shear rate from that shear rate step profile. And continue on that stepwise fashion, waiting for equilibrium each step. That's it's the most ideal way to get the highest quality data when you're doing a study over viscosity over a wide range of shear rates. So typically, one metric that we measure most commonly with rheology is viscosity. And we do make viscosity measurements in a rotational fashion, right? We're rotating that top plate or cone or the inner cylinder in a unidirectional way. We're just rotating at different speeds and measuring the viscosity. But as we kind of discussed today, not all samples are ideal for this type of measurement. Some samples actually come out of the gap like we talked about due to some elastic effects like polymer melt. Actually, this elasticity will actually make rotating geometry lose contact with the sample. So commonly when we're working with robust samples, pastes and gels, we'll actually get slipped. So the rotating geometry will lose contact with the sample and will eventually just be rotating and measuring a friction between the rotating plate and your stationary sample. So very robust samples like really putty peanut butter type materials are very difficult to measure in a rotational fashion. And then if you're interested in the sample structure, so you're dealing with emulsions, gels, or possibly the curing behavior of the material, well, understand its structure. The rotation measurements are not ideal. You want to go towards oscillatory type measurements. And also, rotational is not good for studying the long-term stability of a structure as well. So what happens when you're doing a rotational study, depicted here with the eggs, is when you're doing a rotational measurement, you're actually breaking down the structure and you're pulling apart the individual components. As shown here, you're scrambling the eggs, you're breaking up its structure. However, an alternative method is doing an oscillatory measurement. It's basically your head, instead of rotating around unidirectionally, it oscillates back and forth and basically just stretches and deforms your sample, and you monitor how that sample responds to that deformation. So an oscillatory measurement here leaves the structure undamaged. Okay, so the example of our eggs, the egg yolks, the egg white, they remain intact. You're not breaking those down. So after an oscillatory measurement, you regain that structure. Okay? And doing an oscillatory measurement, what it allows you to do is actually study the stability of an internal structure. So if you have these emulsions and gel type setups, you can actually study this internal structure and how stable it is over different input stresses and strains. So with an oscillatory measurement, you get a parameter that's called modulus. And you can break down that modulus into its elastic components, which is G prime, which represents how solid or elastic-like the material is. Or you can get G double prime here, which is actually represents the viscous components within the material. The G prime, the solid-like behavior of the material, is represented in the filled symbol. The viscous or flowable portion of your sample is represented in open circles here. So we looked at the structure stability of 3 different cosmetic products, looking at their viscous and elastic modulus as a function of input deformation. So essentially just stretching those materials more and more and looking how robust the structure is. So looking at the cream and lotion examples here, they're both initially elastically dominated. So the filled circles, which is the elastic modulus, is more dominant than the viscous modulus. Okay, so we apply low deformation, just slightly stretching those materials. They behave like solids, right? They have elastic material, so cream and lotions, they sit up like solids in our hands. But as soon as we apply enough forces, that structure begins to break down, and eventually we get to a point where it breaks down enough that that material will begin to flow. So out here, the high deformations, the lotion and cream, actually behaves more like a viscous liquid. Okay, so you can see the viscous response is dominating the elastic response here at high deformations. Okay? So you can use this type of measurement to just look at the stability of emulsions, gels, paste-like materials, foams, and the stability against materials that might have a tendency to settle out. And the stability of the structure can be related to a yield stress. So, and then you can use the stability of these structures to actually relate it to how it's going to perform in the actual real end-use application. Another way to use oscillatory measurements is to monitor how a structure develops. Okay, this example is milk with an added enzyme, and we're now again measuring the elastic and viscous modulus as a function of time. So our viscous response, or our liquid type portion, here is depicted in blue, and then our elastic response is here in red. So initially, our milk, which is a flowable liquid with just the early introduction of the enzyme, is a flowable viscous liquid. Okay, so our viscous response is greater than our elastic response. It's a flowable material. However, as the reaction goes on and the enzyme begins to work on that milk, it begins to thicken up and eventually get to what's called a crossover point, and our viscous and elastic responses are then equivalent. As that reaction continues to develop, we get to the point where now the material has transitioned from a viscous liquid to an elastic solid. So now at long reaction times, we see a full transition of a material from a flowable liquid to now an elastic gel. So we use oscillatory measurements to study these types of structural developments and reaction type behaviors. You can think about, you can use oscillatory measurements to study the curing of adhesive, gelation studies of proteins, polymer reactions, such as adding cross-linkers to a polymer, the crystallization of fat material, which happens commonly in food application, or even the crystallization set up within a polymer matrix. So remember, oscillation type measurement does not affect the structure development or network formation in some of these phase transition or reaction type systems, and you can provide invaluable insight into the material structure by just probing it using oscillatory measurements and not breaking down that structure. So that leads us to the end of today's webinar. You kind of know going into today that rheology measurements can be challenging, right? Especially for the novice user, but reliable results can be achieved when we take the right precautions, right? We're selecting the right geometry for our material and for the measurement procedure. Sample is handled very carefully. If it's fragile, we're scooping it. We're being very gentle when we lower the head. We're trimming it carefully. And then we select the right measuring method for our material. Just remember, there is no universal geometry or test method to handle all materials under the sun. Okay, we need to design our test method and geometry specific to that material or the material parameter that we want to characterize. Again, measuring method should be more than one dot, especially when dealing with complex materials. Remember, viscosity is a dot, not a dot. The method should be adjusted and adapted to the response time of the material, especially at low shear rates or low deformation. And sometimes an oscillatory measurement is more appropriate for our material. Okay? And by keeping all of these things under consideration, we're now on the path to better results. Thank you again for all of your attention, and I will pass it back over to Trevor.
Well, thanks very much, Nate, and I believe we will go directly to our question and answer session. For those of you who may have joined us late, if you have any questions for Nate, you can ask them simply by typing your query into the question box, which is located at the bottom left-hand side of your screen. So Nate, the first question I have asks, if I have a new user in the lab, how do I ensure they're running a test properly?
Yeah, that's a common challenge, and that goes across, regardless of the type of measurement you're performing. I would say from our end, our instruments and then the Reoloji software that I've talked about quite a bit throughout today's webinar, is they're kind of designed for kind of that novice user. So they're very easy to use, and some of the functionalities that they incorporate is both the instruments as well as the software automatically recognizes any geometry that you might hook up to the instrument. So if you have a new user in the lab and they're going to run a test, you want to make sure that they're using the appropriate geometry for that measurement routine, or you standardize that routine for a given geometry. Well, the instrument as well as the software will automatically recognize, so you don't have to worry about the end users picking the wrong geometry from this drop-down menu, and then it's going to use all of those stored information about that geometry to calculate rheological parameters like viscosity. Also, within the Reolin software, like we saw today, you can actually load images and videos into your measuring procedure. So you can use images of how to properly load a sample or transfer it from a storage device, or how to properly trim the sample, or actually how to properly clean up the geometry after a test. And you can load those images or even a video into the software that will pop up and show that novice user as they're running a test how to properly transfer samples. And you can even have notes and messages built into that procedure. So you get to the point where you need to load the sample, actually have a message that pops up in that measuring procedure that says load the sample now, or trim the sample now, or clean the sample now. Also, another nice feature of the software that helps some of the new users is you can actually, as part of your measuring procedure, load up in a historical data file that will actually show on the screen as you're collecting live data. So as you're collecting live data, it'll plot that newly collected data versus a historical data file, so that new user can know instantly if its new collected data represents some historical data. So if that test is off to the right start, the data is comparable to historical data collected in the past. Gives the new user confidence as well as the manager, senior lab technician, who doesn't have to be in the lab at all times to make sure tests are running properly.
Excellent, thank you. Now, our next question asks, what if removing a material from its container destroys its structure? How would you test that type of a sample?
Yeah. That's challenging, especially with these very delicate, fragile samples that have these very sensitive structures. So one option that we have with our products is what we call our universal vessel holder. So it actually fastens itself into the rheometer, and you can actually take a measurement of the material in its storage container. So you actually have to take the material out of its container to measure its rheological profile. So this universal vessel container fastens to the rheometer. You then securely mount that storage container into this universal vessel holder, and then you can measure that rheological profile. This universal vessel holders can adapt to any size container, from small jars, cans, even little beakers in the lab, to large, even buckets, gallon buckets of material you may have. And lock that in, lower the measuring head into that large device, and you're off and running to measure a device or measure material behavior without actually having to physically remove it from its storage container.
Excellent, thank you. Now our next question asks, I have a low viscosity material that I test using concentric cylinders. Do you have any suggestions to improve the cleaning process?
Yeah, that's one of the biggest challenges with concentric cylinders. They can be quite a bear to clean, especially with certain materials that are quite thick or sticky. One benefit of our kind of concentric cylinder setup is all of our cups or outer cylinders have a bottom that unscrews. You can unscrew that bottom and you have access to your sample from the top and bottom. You can clean from the top or the bottom, or use some sort of cleaning device like a plunger, basically squeeze pressed material out through the bottom. So you have better access and it's easier to clean. If you have really tough materials to clean, they're just wasting too much time, or it's just too much of a bear to get that outer cylinder clean. We also offer disposable cups, so that can be an option, which that way you can just dispose the sample and the cup at the end of the test and throw it away. If neither one of those are a great option, or you're still having problems cleaning, you can also just try soaking the cup overnight with different solvents, or even using a sonic air or a sonic bath to dislodge some really stuck material.
Excellent, thank you. Well, Nate, as I look at the clock, I realize we are running low on time, so I'd like to thank you for your presentation today. And to our audience, if you have any further questions, please consider reaching out to Nate directly. His contact information, as you can see, is available on the screen now. And this brings us to the end of today's webinar. Just a reminder that this webinar was recorded and you will receive an email notifying you when the on-demand video is available. On behalf of Lab Manager, I'd like to thank Nate Crawford for joining us today and Thermo Fisher Scientific for sponsoring this Product Spotlight webinar. This concludes today's Product Spotlight. I'd like to thank all of our attendees for taking time out of their busy schedules to join us today. And if you'd like more information on all of Lab Manager's upcoming and on-demand webinars, or to learn more about the latest laboratory tools and technologies, I invite you to visit our website at labmanager.com. Thank you for joining us, and have a great day.